Hello, am I audible now?
Yes, sir, you're audible.
Yeah, just a second.
So I'm not able to message you now.
Just a second. I'm just trying to fix this. Yeah, Anurag Bijia. Can you hear me, Anurag? You there? Anurag, please respond. Yeah, Anurag. What you do, you just leave this meeting and then rejoin. Just do this once. Yeah, guys, can you hear me? I think it's fine now.
Yes. Sir, I still can't message you. It says Gaurav sir is not in the meeting. Gaurav Sinha is not in the meeting.
Is it? I am in the meeting, no?
But sir, I'm not able to message you.
Some problem. Try now. Everyone can.
No, sir, I still can't.
Pranav, right?
Yes, sir.
See, everyone is texting me. I think, Pranav, what you do, you just also leave the meeting and join again. And then you check.
Okay, sir.
Just 2 minutes, we'll start. Yeah, Pranav, it's fine now. I think it's fine. Yeah. Yes. So guys, last class we have discussed about resonance. Okay. And how to draw the resonating structure. Yes, Pranav, go ahead. Pranav, structural isomerism, we won't discuss here. Okay, we can discuss in, you can text me that out. Okay, I'll see over there. Right? Okay. So last class, we have discussed resonance, and we have seen what are resonating structures, and aromaticity also we have discussed. Yes or no? Yes, we have also discussed aromaticity. Fine. Okay, so next we have to start with the next this thing, electronic effects, and that is hyperconjugation. We'll see the application of resonance, okay, after finishing hyperconjugation. Aromaticity we haven't done. Tell me guys, aromaticity we haven't done last class. Acha, fine. Then we'll do it now. I thought I've done. Okay, fine. So I guess, correct me if I'm wrong. I think we have discussed resonance, resonating structure, how to draw resonating structure. Yes? Fine. Okay. So next we'll start with aromaticity. Heading right down aromaticity. Okay. Yeah, that's right. Got it. So heading, all of you write down aromaticity. Just you need to know few conditions here of aromaticity, and on the basis of those conditions you can do this kind of questions. Okay. Aromaticity is what? Aromaticity is the property of, write down, it is the property of cyclic conjugated system. Cyclic conjugated planar compounds. Planar compounds or system. System means compound only here, right? It is a property of cyclic conjugated planar compounds or system. Aromaticity, it provides extra stability to the molecule. There are three types of compounds we have here. No, it is the application of resonance actually. Okay, aromaticity you can understand once you know what is resonance. Okay. Now, on the basis of this, we have three types of compounds defined on this. The first type of compound, we call it as aromatic compound. Second type of compound we have anti-aromatic compound. Anti-aromatic compound. And the last one we have non-aromatic, we'll discuss after this too. Okay. Now the question that you are going to get here is some compounds to be given. You have to identify whether the given compounds is aromatic, anti-aromatic or non-aromatic. That is it. Okay. Right. In KVVY, they won't ask tough questions on this. Direct question they ask, which you can find out based on the condition. Okay. There are few conditions on which, on the basis of that, we can find out which compound is aromatic or anti-aromatic or non-aromatic. But there are also some compounds which does not follow those conditions, but is still aromatic or anti-aromatic. Means exceptions are there. But those things we are not going to do. It is not, there in KQ exam. Only basic understanding of these three compounds you should have. So we'll only focus on that. We'll see enough number of examples so that you will understand how to find out the given compound is aromatic or not. Okay. Fine. So what all conditions we have for an aromatic compound? The first condition is the molecule must be cyclic. Acyclic compound can never be aromatic. The second condition we have, it must be planar. Third type we have conjugated system. Conjugated system we have discussed last class. And fourth type, that it follows Huckel's rule. Huckel's rule. Now, what is Huckel's rule? Huckel's rule says that the cyclic molecule has 4n plus 2 pi electrons. That is it. If you count number of pi electrons, and that is 4n plus 2, right? It means it follows Huckel's rule, where n can be any number, 0, 1, 2, and so on. Any number. These are the 4 conditions you need to check. That is it. Nothing much. Okay. Now we'll see the simplest example of aromatic compounds. What is this compound? I guess all of you know this. What is this compound? No. There's no derivation of Huckel's rule. It's just an Anurag. It's just an observations. There's no derivation of Huckel's rule. Okay, so that is benzene. Correct. Now, does it satisfy this condition? Is it cyclic? Yes, it is cyclic. Is it planar? All the carbon atoms are sp2. Planar. It is conjugated system. Yes, it is conjugated system. Pi sigma pi conjugation is there. Follows Huckel's rule. How many pi electrons we have here? Could you tell me? Right? It has 6 pi electron. So does this follow Huckel's rule? Yes, it follows. For n is equals to? For n is equals to 1. Very good. So for n is equals to 1, it is 6 pi electron. Hence the molecule follows Huckel's rule and it is aromatic. That is it. Nothing you have to do much. For planarity, you just need to check all the atoms, carbon atoms must be sp2 hybridized. All the carbon atoms must be sp2 hybridized. Anurag, you see, total pi electrons we are getting 6. So in that formula, 4n plus 2, if you substitute n is equals to 1, you'll get 6 pi electron. Hence, n is equals to 1. Conjugated system, Shreyas, I have discussed last class. Okay. You were there in the last class, Shreyas? N is any number, any whole number, 0, 1, 2, 3, 4, 5, and so on. Right? You check your notes, conjugated system I have explained. I cannot discuss conjugated system now. There are so many things. Okay, just give 1 minute and just check. Conjugated system I have discussed last class. 6 types of conjugated system I have told you in the last session. Did you get it? So for planarity, what you need to check, the carbon atom must not be sp3 hybridized. That is it. There are some more some more points we have in this. With example, we'll try to cover that. All of you, did you understand this? Clear? You can type CLR, all of you, quickly. Correct. We'll do enough of examples. Okay, you will be able to understand it clearly. Okay, first we'll understand the 3 terms and then we'll see examples. Now you see, like aromaticity, anti-aromatic compounds also have some condition. And what is that condition? You see, the first 3 condition is exactly same. Means it is cyclic, planar, conjugated. Conjugated system. First 3 conditions are same, but the second one, it has 4 n pi electron, not 4n plus 2, where n is again any number 0, 1, 2, 3, and so on. Anurag, your question, why it is 4n plus 2, why not 2n? You will get it. We'll do some example, you will understand it. Got it? Now, you see this example for this anti-aromatic compound. Is it cyclic? Yes. Planar? Planar? Yes. Conjugated? Pi sigma pi conjugation, right? How many pi electrons? 4 pi electrons. So it follows Huckel's rule for anti-aromatic compounds, 4n pi electron, right? N is equals to 1. Hence it is anti-aromatic. So now Anurag, you see with 2n, if you are saying, so with 2n, this compound should be aromatic, yes or no? Which is not the case. It is anti-aromatic compound. The actual behavior is anti-aromatic. For Huckel's rule, you see, Huckel's rule is given for aromatic and anti-aromatic compounds. According to this, anti-aromatic compound should have 4n pi electron. Aromatic compound should have 4n plus 2 pi electron. Okay. Now you got it. Why it is not 2n pi? Anurag, clear? See, Pranav, we can discuss this also, how aromatic compounds are different from anti-aromatic. The actual reason we can understand, but for that you should know the concept of orbital. Okay, if you ask me, I can say the orbital that forms here has unpaired electron in anti-aromatic compounds. But in aromatic compounds, all the electrons are paired. That's why it is highly stable. Anti-aromatic compounds are not stable compounds. Okay, I'll come to that. But I don't want to go into that orbital concept, okay, because we haven't done that orbital thing. Okay, that's why I'm giving you the information which is required. Okay, in terms of chemical properties, you have to see the stability order of all this. That I'll give you the stability order, okay, and then you will get it. Okay, so this is the second type of compound we have. third type of compound we have in this, that we call it as non-aromatic compound. Non-aromatic compounds are the normal compounds which has normal stability. Like for example, you see the condition for this, it is not cyclic, or if cyclic, then cyclic but not conjugated. Not cyclic or cyclic but not conjugated. Example, you see, it is a non-aromatic compound. This one you see, conjugated but not cyclic, again non-aromatic compound. It is cyclic but not conjugated, non-aromatic compound. Okay. This also you see, cyclic but conjugation we'll have till here. This is sp3, again non-aromatic, non-planar it is. Okay. This compound you see, sp3 here. So not conjugated, it is again non-aromatic compounds. In the given cyclic structure, if any carbon atom is sp3, it is non-aromatic. Ring structure it is. Clear? Yes, there should not be any sp3. If it is sp3, then orbitals are not vacant and conjugation is not there. Yes, you can say that, Siddhant. Yes, correct, Madhav. sp3 non-planar. Second last one is conjugated till here. Means there is conjugation from this carbon to this carbon. This part is not in conjugation. Hence it is non-aromatic. Yes, we have from here to here. This part is not in conjugation, hence it is non-aromatic. Conjugation should be there in the entire ring. Otherwise it is non-aromatic. Clear? No, number of pi electrons you don't have to count. You just check whether there is any sp3 hybridized carbon or not. If it is there in the ring, then it is non-aromatic. Simple. Number of pi electrons we don't count in this. Number of pi electrons we count only in aromatic and anti-aromatic compounds. Clear? Tell me guys, understood? Can resonance be there in non-carbon containing compound? Yes, possible. If there is other atom also, resonance possible. I'll show you the example, Madhu. Okay. Aromatic compounds, aromaticity, like I told you now, it is the property of a molecule. Aromaticity is the phenomenon, right? And the property which provides extra stability to the compound, right? Okay. Now, overall, what happens? Like if you see this, the exact thing of this, that in this what happens, in non-aromatic compounds, molecular orbital does not form. Okay, now you do not know about all this. What is molecular orbital and all? That's why I'm not going into that. Okay, but the information I am giving you, I'm telling you, this is enough for you to solve the question. Okay, that's why those, how it is different from each other. That part I'm not going to discuss here. Okay, you will get confused. Okay, now one thing you see, aromatic compounds, you can say it is the most stable compound. The stability order is aromatic is most stable. Then we have non-aromatic. And in the last, we have anti-aromatic. Least stable is anti-aromatic. Most stable means least energy. Anti-aromatic, maximum energy. Energy order will be reversed. Okay, you just need to understand here, for a given compound, how do we identify that it is aromatic, non-aromatic, or anti-aromatic? That is it. Okay, can we see some example here? This stability order, they have asked many times in all exams actually. NEET, JEE, BITSAT, all exams they have asked this question. Means energy is maximum for this anti-aromatic compounds. We have energy levels, no? The one which is least stable has maximum energy. No, it's not charged. The energy, total energy. Means suppose any object has some potential energy, no, at some point. Right. Similarly, compounds also have some energy because of the transfer of electron from one point to another point. Overall energy, if it is least, it is most stable compound. Yes, electron dislocation, electron delocalization, not dislocation also you can say. Electron dislocation provides, delocalization provides more energy, less energy to the molecule, more stability. Breaking down into smaller molecules, it consumes energy. But here we are not talking about what happens when you break down the molecule into equal halves. No, breaking of anything requires energy, takes energy, and then suppose if you want to break the pen, right, you have to provide energy. Non-aromatic compounds, the energy falls in between. Anti-aromatic is the maximum, then we have non-aromatic, then we have aromatic. Energy order is this. Non-aromatic compounds has more energy than aromatic compounds. No, more dislocation means less energy. Yes, Anurag, that's right. More transfer of electron, more will be the stability, and less will be the energy of the molecule. Yes, it's possible. We'll do examples, Pranav. We'll do. See, potential and kinetic energy, we do not say. Overall energy, because electrons are involved, no? So there is many different kinds of energy. We have rotational energy, kinetic energy, potential energy, nuclear energy, all those energies are there. So we don't specify the energy term. Instead, we say energy maximum or minimum, total energy, overall energy. Yeah, I'll do that. Just if you let me do, then if you let me give, then I'll give that example, right? You're asking doubts, I'm explaining your doubts. That is it. So let me finish the doubt first. We'll take the example. Okay, any other doubt? No. Can I move on to the example? Correct? Okay. Now, so question that you get in the exam, they'll give you structures, like suppose 4 options will be given. Which compound is aromatic? This kind of questions you may get. Which compound has maximum energy? This question also you may get, or minimum energy. This kind of questions you may get, right? So basically for all these type of questions, you need to identify the given molecule is aromatic, non-aromatic, or anti-aromatic. Correct? Okay. Let's do some example here. First one. Only ring structure you have to consider. Okay, suppose this methyl group, you don't have to consider this because cyclic compound you need to consider. We don't have to do anything with parent chain Anurag here. Aromaticity is only for cyclic compounds. So we need to consider cyclic compound only. You don't have to check what is the parent chain here. Tell me these compounds: aromaticity, anti-aromaticity. I'll share Charan. Okay. Okay, now see I'm doing, did you draw all the structure? Okay, shall we start? Did you draw all the structures? Okay. First compound you see, we have discussed this. It has 6 pi electron and aromatic in nature. Like I said, you have to take only ring structure. So it has 4 pi electron, anti-aromatic in nature. This has sp3, it is non-aromatic in nature. This carbon atom is sp3, hence it is non-aromatic, no conjugation in this. In this we have pi sigma positive charge, conjugation is there, right? And number of pi electrons is 2 pi electrons, follows Huckel's rule for n is equals to 0, aromatic in nature. Again we have conjugation, 4 pi electron, it is anti-aromatic in nature. We have conjugation here, 6 pi electron, aromatic in nature. Remember, when we have lone pair present like this, that lone pair we also count in pi electrons. Because when you draw the resonating structure, this comes over here and this comes over here. So lone pair converts into pi, pi converts into lone pair. So we also count lone pair in the number of pi electrons. Clear? So here we have 1 pi, 2 plus 2, 4 plus 2, 6 electron. 2 plus 2, 4 electron, right? Here we have 2 electron pair, 2 pi electron, aromatic for n is equals to 0. This one, this carbon is what? sp3, so it is non-aromatic. Could you tell me this one? Next one you tell me. We have conjugation, positive charge, 2 plus 2, 4 pi electron, cyclic conjugated system, anti-aromatic. Okay, 2 plus 2 plus 2, 6 pi electron, aromatic. This carbon atom is sp3, so it is non-aromatic. Okay, this one you see, the oxygen has 2 lone pair of electron. But out of 2, we count only 1. Both we won't count, right? So 2, 4, 6 positive charge. So 6 pi electron, aromatic in nature. Yes, yes, correct, mother. Here also we have 2 lone pairs. We count only 1. 2, 4, 6, 8 pi electron. It is anti-aromatic. This nitrogen has lone pair, but this lone pair is not involved in resonance. 2, 4, 6, 6 pi electron, aromatic. This lone pair is not involved in resonance. This nitrogen, this lone pair is involved in resonance, 2, 4, 6 pi electron. This is also aromatic in. In the last two, The last one, the lone pair is involved. Second last one, the lone pair is not involved. I'll explain that. I'll explain that straight. Just a second. Okay. See, first of all, when do we take lone pair into the count and when we do not take, that you should know. One note you write down in this first. Write down, if the lone pair present on sp2 hybridized nitrogen atom if the lone pair present on sp2 hybridized nitrogen atom, then it is not involved in resonance and we don't count it. Okay, and it is not involved in resonance and we don't count it. Okay, sp2 hybridized nitrogen, the lone pair is not involved. Next line, write down, for oxygen, out of two lone pairs, only one lone pair is involved in resonance. Right, for oxygen, out of two, only one lone pair is involved in resonance. We have reasons for this also. Why not both? Why only one? Right, why not both? Why we have only one? Okay, we have reasons for this also. But if you keep these 2 points in mind, you can do all these questions. Okay, now you see this nitrogen atom here, it is sp2 hybridized. And hence this lone pair we are not counting. We are counting only 2, 4, 6 electron. Yes, correct, Anurag, correct. sp hybridized not possible in ring. Triple bond possible in ring when we have at least 8 membered ring. In the smaller ring, it is not possible. Correct? It is sp2, hence this nitrogen is not, lone pair is not involved. Now this is sp3, so this is involved in resonance. You see, you can draw the resonating structure this way. And then again, this lone pair comes over here, this pi electron comes over here, and so on we can draw. Okay, so this 6 pi electron is because of 2, 4, 6. The name of this compound is pyridine. This is pyridine. The name of this compound is pyrrole. Okay, if you look at the basicity of this nitrogen and this nitrogen in pyridine and pyrrole, which one is more basic? Okay, which one is more basic? You see here what happens. Basic nature is the tendency to lose lone pair of electron, correct? Basic nature is the tendency to lose lone pair of electron, and lone pair the atoms can lose when the lone pair is available on it. Okay, this lone pair, you see, it is not available on nitrogen atom. This is involved in resonance. So this lone pair, what we can see, it is delocalized. The term we use here, it is involved in resonance, hence it is delocalized from one point to another point, and then another point, another point, through resonance. But this lone pair is not involved in resonance. This lone pair is localized. It is available on the nitrogen atom. So when it is available on nitrogen atom, the pyridine can release this electron, right? Donates this electron pair. Hence, the basicity order of pyridine is more than to that of pyrrole. Is it clear? In pyridine, it is not 3 degrees Celsius, 2 degree only. Now you see one thing here. This is basicity order of pyridine is more than to that of pyrrole. It is because of aromaticity, correct? No, it's pyridine only. Pyridine. Okay. Basicity of pyridine is more because of aromaticity. Now, if you talk about electronegativity, which nitrogen is more electronegative? This one or this one? A or B? Which one is more electronegative? Obviously, A is more electronegative because A has more percentage S character, sp2 hybridized. Yes or no? Tell me. A is more electronegative. So the one which is more electronegative, it has less tendency to donate electron, right? So when you take electronegativity as the factor, then the answer will be reversed, right? So in this kind of cases, you should know which factor is the dominating factor. So aromaticity always dominates the other factor actually. That's why the answer will be according to aromaticity. Pyridine is more basic than pyrrole. That is it. Clear? Any doubt? Yes, both are aromatic. Pyrrole is aromatic because of the lone pair involved in resonance. This one is also aromatic, but not because of this lone pair. Hence the order is. Because their hybridization is different, Himanshu. Because of hybridization, we have different percentage S character and hence different electronegativity. Did you understand this? See, in pyridine, what happens? First of all, both, see, again, I am repeating it. Listen to me carefully. Both compounds are aromatic compounds. Done. Pyrrole is aromatic because of the involvement of this lone pair. Right? So this lone pair is actually, it is continuously moving over the ring, like we have in benzene. Electron clouds are continuously moving. Similarly, this lone pair is also continuously moving over the ring. It is not available on nitrogen atom. And when the electron pair is involved in resonance like this, we call it as delocalized electron pair. It is not available on nitrogen atom. Here, this one is also aromatic, but not because of the lone pair, because of this pi sigma pi conjugation. So this pi electrons are involved in resonance. So these electrons are also delocalized, but this electron pair is available on nitrogen atom because it is not involved in resonance. So when it is available, it can donate. Hence, this one is more basic. This is not available, it cannot donate, hence it is less basic. Clear, Pranav? Okay, so basic nature comparison of pyridine and pyrrole is very important. I'll give you one more example of this basic nature comparison. Tell me the basic order of A, B, and C. Why C is the most basic? Least electronegative. That's right. Okay. So now you see this nitrogen is sp2. This nitrogen is sp3, but lone pair is involved in resonance. This lone pair is available. This is also sp3. So obviously this lone pair is involved in aromaticity. So B is the least basic we have. In this two, right, lone pair is available on nitrogen atom, but this one is sp2, this one is sp3. So order of basicity is this. Tell me the aromatic behavior of this compound. Aromatic, non-aromatic, or anti-aromatic? Done? Okay. Now the first compound you see, oxygen has two lone pair, but we count only one. So 6 pi electron, aromatic. Okay. This nitrogen has one lone pair, and this nitrogen also has one lone pair. This nitrogen, one lone pair, one lone pair, one lone pair. Could you tell me the number of pi electrons here? In this one, again you see this nitrogen atom is sp2 hybridized, correct? So this lone pair is not involved in resonance. So we have 6 pi electron here, aromatic again. Okay, this one again, you see all the nitrogen atoms are sp2 hybridized aromatic. Understood? What, Shreyas? I didn't get you out. Where is sp? sp2 does not mean it's non-planar. sp3 means it's non-planar. Shreyas. Yeah. Okay. Yes, linear also it's fine. Anurag. Linear also is fine. Yes. Yes, can say that. Lone pair, if it is conjugated, we can consider that as linear. No, where is sp hybridized? We don't have sp hybridized in B. This nitrogen atom is sp3, sp2, 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 sp2. No, it is sp3. By mistake, I have written. Okay. Now you see in this question, what they do, they have asked this question once. That suppose this is alpha nit means suppose this is first compound, first nitrogen, and this is second nitrogen. Like this, some notation is given. Which one is more basic here? First nitrogen or second nitrogen? Obviously, second nitrogen is more basic. N2 is more basic than N1. Why? Because N2, the lone pair of electron is localized. It is present on the nitrogen atom. But this lone pair is involved in resonance. Hence, this one is more basic. Yes. So is it clear? Any doubt in this? We have discussed plus M minus M also. Plus M minus M we have discussed. No. Okay. Okay. Now you see in this resonance effect or mesomeric effect, like inductive effect also, we have electron releasing groups and electron withdrawing group. Like we have plus I and minus I. So plus means what? Electron releasing or electron withdrawing? Plus means electron releasing. So plus I is electron releasing. So here also plus M or plus R is electron releasing. Okay. Like inductive effect, here also we have electron releasing groups and electron withdrawing groups. So like plus I, here we have plus M effect. Minus I, here we have minus M effect. So plus M effect means electron releasing effect. Minus M means electron withdrawing effect. Okay. Now you look at some examples on this. Heading you write down plus M minus M effect. Okay. So plus M effect or plus M group, we also call it as plus R group. Both are same thing. Plus M or plus R, both are same thing. Okay. So plus M groups are those groups resonance effect and mesomeric effect are the same thing. Both are the same thing. I have told you this. Resonance or mesomeric effect. Both are same. Plus M means plus R, minus M means minus R. That is it. Okay. So plus M or plus R groups are the groups which releases electron. Sorry, which releases electron. So electron donors are plus M or plus R group. Okay. How do we know that what all groups are electron releasing group and what all groups are electron withdrawing group? Correct. Consider this benzene ring, and on this benzene ring one group is attached, any group. No, meso compound is different, Shreyas. It is different. Don't compare these two. Okay. Now with respect to this group, you see, no. I told you, no, this mesomeric effect is nothing but resonance effect. Okay. So we have electron releasing as well as electron withdrawing group also. So plus means always electron releasing. Correct. Now we are going to see what all electron releasing group we have and what all electron withdrawing group we have under resonance. Got it? Hyperconjugation is different. We are doing resonance only now. Correct, Anurag? Yes, the difference in inductive effect and resonance is here we have pi electrons or lone pair involved, but there we have only sigma electrons involved. Mesomeric effect, I told you so many times, mesomeric is just a name. It is same as resonance. Both are same thing, two different names. That is it. Yes, it is for only resonance. It is for only resonance. Aromaticity we have done. that you let it be now. This is the next topic we have in resonance. Aromaticity, we are done with it. See, wherever resonance is there, it is applicable. Wherever resonance is possible, plus M minus M group is there, it is possible. It just requires conjugation, that is it. We are going to discuss here in aromatic compounds because this benzene is an aromatic compound, but it is applicable for all the conjugated systems. What happened? Any other doubt? I'm waiting. I have clearly mentioned that plus M minus M group is applicable in all the compounds where resonance is possible. Anything else? We are taking here this compound, benzene ring, but it is possible in all the molecules where resonance is possible. Go ahead, Pranav. Pranav, I saw your question. Okay, let it be. That part you let it be. If you see, if you keep on assuming things, no, if we have this, if we have that, then what happens? Like this, we won't stop anywhere. There are thousands of questions possible like that. Okay, so let us understand the concept first. You do not even know what is plus M or minus M, how it is affecting the stability. So first, let us discuss this. Okay, first let's understand, and then we'll see the questions. Okay, the application part of it. We cannot directly jump into the result. Okay, what happens? So wait for some time. Okay, now can we start this? Okay, now suppose we have a benzene ring, correct, and a group attached with it. This group can be plus M group or minus M group, which we can also say plus R group or minus R group. Okay, we'll see that. With respect to this group, this position, what we call it as, I have discussed this already in nomenclature. What is this position? This is ortho position. Remember, what is this position? This is meta position. And this is para. Okay, this is again meta. And this is again ortho. So first thing that you should know, we have two ortho, two meta, and one para position. That is one thing. Now, what happens with this group when attached to the ring? Then what happens at these three positions that we should know? Correct? Okay. Now you see this example. Suppose we have a ring, benzene ring, and we have a group present on it, OH. Correct? Now you see this OH, oxygen has two lone pair on it. That we already know. Do we have conjugation here? Pi sigma lone pair conjugation? This side? Yes, we have conjugation. Yeah, tell me. We have conjugation, right? No doubt. Okay. Now what happens with this, you see? If you drop the resonating structure, this lone pair comes over here and this pi electron jumps onto this carbon. So what we get, you see. The structure that we get here, I am just drawing the resonating structure, nothing else, that we have already discussed last class. We have a double bond O, H, positive charge. Here we get the negative charge because pi electrons shift onto this carbon atom, and this is the 2 pi. Now, next is what? Again, we can draw resonating structure. This comes over here, this pi electron jumps onto this carbon. So what we get is this. OH positive charge. Can we draw another structure? Which is this. And one more structure is possible when this pi electron comes over here, this jumps onto this oxygen. Now tell me, anyone has doubt in this structure? How do we draw the resonating structure? Last class we have discussed this. Correct? Okay. Now you see what is happening here. We have a ring and a group attached to this ring. And this group is releasing electron, yes or no? It is providing electron to the ring. Correct? Can we say that? Because this lone pair is coming over here into this ring. So this is electron releasing group. Is it correct? Okay. And because of electron releasing group, which shows plus M effect, this electron releasing nature that we have, it is plus M nature of that group. Means we can say this OH group, hydroxy group, shows plus M effect. Correct? Hydroxy group shows plus M effect. So this lone pair comes into this bond pair and pi electron jumps over here. So what happens at ortho para position? We are getting negative charge, right? At ortho position negative charge, para position negative charge, again ortho position negative charge. Means according to this, like because of this electron releasing nature, or what we can write because of plus M effect, plus M nature, or plus M effect, electron density at ortho and para position increases. Okay, meta position there is no effect. So meta position is unaffected. Okay. Is it clear? Any doubt in this? Because of this, since meta position is unaffected, then if any group attached over here, any group attached at this position, meta position, at meta position, this group, suppose we have OH here, and this some group is attached. So this groups always shows or only shows inductive effect. inductive effect. Why? Because resonance does not affect this position. Since it is connected to this, so it can show I effect, but resonance effect it does not show. Resonance effect is possible at this position and this position. Plus R or plus M possible. Minus R or minus M possible at this two position. Okay, we'll take some example. You will get the better understanding of this. Just you keep this in mind. We'll take some example of it. Okay, but before going into that, we should know what all group shows plus M effect and what all group shows minus M effect. Okay, now you see for plus M effect, what we need, we must have at least lone pair on the atom which is attached to the ring. Then only it will donate this lone pair. If lone pair is not there, then what this group will donate to the ring? Nothing. Are you getting it? Right? So the condition for a group to show plus M effect is what? Write down. The condition for a group to show plus M, the condition is the atom with which the group is attached to the ring, the atom with which the group is attached to the ring must contain at least one lone pair. Must contains at least one lone pair. Did you write this? Condition is the atom with which the ring is attached must contains at least one lone pair. Now you see what all groups are plus M group. I'll write down some example here. Plus M group condition I have already given you. Nothing you have to memorize. Just you should keep this condition in mind. Suppose halogen atom attached to the ring. It has 3 lone pair. Can show plus M. OH attached to the ring. Oxygen has 2 lone pair. Can show plus M. NH2 attached to the ring. Nitrogen has 1 lone pair. Can show plus M. OCS3 attached to the ring. Oxygen has again 2 lone pair. Can show plus M. SH attached to the ring. Sulfur has 2 lone pair. Can show plus M. Okay. OC double bond OCS3. Oxygen has 2 lone pair attached to the ring. Can show plus M. NR2 has 1 lone pair attached to the ring. Shows plus M. NHCOCS3 has 1 lone pair attached to the ring or nitrogen atom and hence shows plus M. Is it clear? Any doubt in this? Yeah, I'll just go back. Just this condition you have to keep in mind. Like I have already told you, for plus M, for plus I and minus I, if you do not know the nature of the group, no order you let it be. We can compare the order, but like I effect, we do not have such order. Okay, you won't get questions on that. Okay, but little bit comparison you can do. I'll explain that how. Okay, so like if the nature of groups you do not know, whether it is plus I or minus I, you cannot do the question. So here also we have the same thing. You should know what group shows what effect, plus M or minus M. So condition I have given you, at least one lone pair must present. Okay, Now, you see the another one that is minus M effect right now. Minus M, which we also call it as minus R effect. Both are same thing. Right on, these are electron withdrawing effect. Withdrawing effect. Electron withdrawing effect is what? I'll show you an example. Suppose we have a ring again, benzene ring. And here we have a group, suppose we have NO2 attached to this group, N double bond O and O, NO2 attached to this ring. See what happens here. Between nitrogen and oxygen, we have a double bond. So pi sigma pi conjugation we have here. And oxygen is more electronegative than nitrogen. So this will drag the bond pair of electron towards the side. So this comes over here and this pi electron jumps onto this oxygen. So the structure that we have here, the resonating structure is this. Double bond N, O, O negative. Right, here we have positive, double bond O. Anyone has doubt in this? Since this pi electron jumps over here, so this carbon will have one positive charge, oxygen will have one negative charge. And then further, we can draw the resonating structure. This pi electrons comes over here. I am not going to draw the entire structure, resonating structure, that you can draw easily. We'll get the next structure is this. Are you getting it? Means oxygen is withdrawing electron, taking electron on its side. Shreyash. Oxygen is taking electron on its own. Correct? So further, if you draw the resonating structure, you will see that the positive charge you'll get here. And positive charge appears on ortho and para position. It means positive charge is coming. It means the electron density is decreasing right now due to minus M effect. Due to minus M effect, the electron density decreases at ortho and para position. This is the first point. Electron density decreases at ortho and para position. Meta position is unaffected. Meta position is unaffected. Okay. Again means what? That any group attached to that meta position does not show plus and minus M. I have given you already that. Okay. Unaffected. Condition for a group to show minus M is what? You see between the first and second atom, we must have multiple bonds. So conditions I'll write down here. Condition for a group to show minus M effect is, suppose this is the atom X attached to the ring, first atom, and with the second atom, we must have multiple bond here. Or we can also have triple bond possible. This is also possible. Or we can also have an atom attached to the ring directly and has vacant orbital on this. This box I have just a symbol. It represents the vacant orbital. This two condition is true if the electronegativity of Y, like we have here, oxygen, is greater than to that of X. Then the group shows minus M effect. I'll write down some examples here. You see, groups which shows minus M effects are, first one we have already seen, NO2 and double bond O. We have CHO, C double bond O, H. We have COOH, C double bond O, OH. We have COCl, C double bond O, Cl. All these you see satisfy the first two conditions. C double bond O, OCS3. C double bond O, NH, pH. pH is phenyl benzene ring. We can have cyanide also, C triple bond N. N is more electronegative than carbon. Or we can have a group like CH2, positive charge, a vacant orbital. Any vacant orbital, vacant D we can have, vacant P we can have, any vacant orbital. P, D, any orbital. Condition Anurag I have written here. The atom which is attached to the ring, okay, must, and the second atom, first and second atom, we must have multiple bond present. And the electronegativity of the second atom is more than to that of the first atom. Done. Okay. Give me a second. Yeah. So, like we have done in I effect, that first you have to assign the effect of the group. What effect is there? And accordingly, we'll find out the answer. So I am writing down some examples here. You tell me what all effects possible, all possible effects we'll see. Benzene ring, and on the ring we have NH2 attached. What effect possible here? All possible effects write down. We have benzene ring and OCS3 attached on the ring. NH, C double bond OCS3 attached with the ring. NH3 plus attached with the ring. Ring we have CS3 attached with it. CHO. C double bond OOCS3. NO2. Cl. Try all these. You have to assign the effect of the groups attached to the ring. Done, all of you? Okay. See this. First of all, you see nitrogen attached with 3 bonds. So it has one lone pair. This you should know. And when the lone pair attached on the first atom attached to the ring, it can show plus M. Carbon nitrogen, nitrogen is more electronegative, and minus I. Plus M and minus I. Plus R is also fine. Okay. This one, oxygen has 2 lone pair. So plus M and minus I, same reason. Nitrogen has 1 lone pair. Plus M minus I, same reason. This one, nitrogen has no lone pair, more electronegative than carbon. So it shows only minus I here. No plus M. Carbon does not satisfy the condition of plus M and minus R, can show only plus I here. CHO aldehyde group, it is minus M. This one is also minus M. This one is also minus M. Along with that, minus I also possible. This one is also plus M because chlorine has and minus I. To some extent, it also shows minus M. Chlorine. Tell me, any doubt in this?
Sir, NO2 is the same as that N double bond O and coordinate bond.
Yeah. The one we have discussed. See,
Okay,
NH3, we have NH3 plus, means nitrogen does not have any lone pair on it. Correct? There is no lone pair on nitrogen. And we have electronegativity difference between this nitrogen and carbon, hence minus I. Shreyas, the DBP has been uploaded on Learnist. Did you check that? Yes, Pranav, just a second. It's there on Learnist. Check once after the class. how NH3 shows minus R. NH3 is this. I'll just show you here. Nitrogen with 3 hydrogen. There's no double bond or triple bond present here, you see? Correct? Okay, so it shows only minus I. Any other one? Do you have any doubt? The last one is, so chlorine is, it has one lone pair. It is one kind of exception we have. Its tendency to show plus M is minimal. Even it does not show plus M effect. Minus I because of the electronegativity of chlorine. Minus M because chlorine has vacant d orbital. Okay. So order for chlorine is minus M and minus I possible. Plus M, very difficult to show. Reason is chlorine is electronegative. It has very less tendency to lose electron. All of you, did you understand this? All effects possible, right? So first we'll assign the effects on the group. Now, one note you write down, all of you. Mesomeric effect dominates inductive effect. Whether it is plus M or minus M, it always dominates inductive effect. So if I ask you the question that what all effects possible here, your answer will be plus M and minus I, correct? But which one is dominating? Dominating effect is plus 1, right? And we'll do the questions according to this dominating effect. Are you getting it? Again, it is plus M dominating, minus I, minus M dominating. Here plus M is not possible. Okay. So if you are considering plus M and minus I, so it's minus I dominates plus M here. It is an exception in case of chlorine. But when minus M we have, then minus M dominates minus I. Apart from this, all other compounds, mesomeric effect always dominates inductive effect. Clear? Okay, the last one you see, what I have discussed so far is in the electronic effects, plus M or minus M dominates minus I, correct? But in case of chlorine, minus I dominates over plus M. That is one exception. Okay, minus I dominates over plus M. So you just need to know the effect shown by the groups. And according to that, you can do the questions. Correct? Now we'll see the application. I'll just write down one more thing here. If you have to find out the acidic order or the stability of intermediate, suppose application of resonance, you see there are many applications, but we are just looking at the important one for KVPY, stability of intermediates. Like we have in carbocation, carbocation stability is what? It is directly proportional to plus I, hence here also it is plus M, and inversely proportional to minus M. If you have carbon ion, then what we'll write? Directly proportional to minus M and inversely proportional to plus M, correct? Is it clear? Acidity order, if you see, acidity order, again it is directly proportional to the stability of what? Stability of conjugate base. Conjugate base. Conjugate base is an anion, so directly proportional to minus M, inversely proportional to plus M. Basic nature is also opposite of it. Are you getting it? Any doubt in this? It is exactly same as we have in I effect. Intermediates, see, intermediates can be stabilized through resonance, no? If you write down this positive charge here, right, this positive charge, so what we say, oh, suppose this one I am writing it down. Here we have negative charge. This is an intermediate carbon ion, right? Now this, because of this lone pair, the compound is aromatic. So it is getting a stability, no? Because of the aromaticity. Right? Or if you write down this, if you write down this one, wait, this one. And positive charge. This is also, you see, positive charge, it has 2 pi electron, it is aromatic. So this is also getting stability through aromaticity, which is nothing but resonating effect, right? So the presence of negative charge or positive charge, that is the intermediate, okay, that also affected by the resonance, okay, like we have in I effect, resonance also affects the stability of carbocation, carbon ion, free radical. No, we'll discuss that. Anti-aromatic plus M minus N, we'll discuss that. Okay, yes. If the aromaticity is there, then plus M minus N, we don't have to consider. It depends upon the given structure also. Here we, like the example I have taken, here you don't have to discuss plus M and minus M. Okay, when we do some examples, you will understand it. Okay, now, just for now, just keep in mind, like I effect, electronic effects also affected the intermediate stability and acidity. Remember in the first class, I have discussed that like I effect is affecting the carbocation carbon ion stability. Resonance also affects this. Hyperconjugation also affects this. Okay, which is the next electronic effects we'll see, right? So in a given question, we have to assign first what effect is there, whether it is I effect, whether it is resonance, whether it is hyperconjugation, and how these effects stabilizes the carbocation or destabilizes. According to that, we'll write down the stability order, right? So just here you see that carbocation stability order is this with respect to the plus and minus M effect and other things I have written. Similarly, it is also related with hyperconjugation. So we'll see first hyperconjugation and then we'll see the example of all the three things together: I effect, hyperconjugation, and inductive effect. Clear? Yeah, is it clear? Correct. Now we'll see first hyperconjugation, and when we do the questions on this, you will get to know how to do the question. And again, I'm telling you this, that solving question is not that difficult. It is the easiest part in this chapter. Only you need to assign effects and order based on that. That is it. Okay. So next effect to write down, hyperconjugation. See, hyperconjugation is a type of resonating effect, right? And we also call it as sigma pi resonance, or no bond resonance, Hyperconjugation is applicable in alkene or alkyne, it is applicable in carbocation, it is applicable in free radical, it is not applicable for carbanion, means it does not affect the stability of carbanion. Only these three things it is applicable for. Okay, condition for hyperconjugation is must have at least one sp3 hybridized alpha hydrogen, means alpha carbon you write down, I'll write down this way, just a second. Must have at least one alpha hydrogen. Alpha hydrogen means this alpha hydrogen must attach to sp3 hybridized carbon. This is the condition. Okay, how to do this, I'll explain. Just copy this down. I didn't explain it, Anurag. I will explain now. Okay, just a second. Yeah, no issue, Anurag, no issue. Okay, now you see we have alkene, right? It is possible in alkene. So I'll take one simple example. Try to understand this. I'll take one simple example, CH double bond CH2, and we have hydrogen present here, you see. Correct? Now you see this is alkene, double bonded carbon atom. Adjacent to this double bonded carbon atom, this carbon atom is alpha carbon. First of all, you need to identify this. And the hydrogen attached to alpha carbon is alpha hydrogen. Clear? It's just a position, Anurag. Like this is alpha. If you attach one more carbon this side, that becomes beta, then gamma, delta, like this it goes. Just a position, yes. The carbon attached to the double bonded carbon atom is alpha carbon. Okay? Yeah, Weber, because I'm telling you that. Okay, you do not know anything actually. It's not about you, it's for all of you. There are many things I am telling you, right? So this is what I'm telling you, this is alpha carbon. That is how we define the position. If you attach, suppose remove this hydrogen, attach one CH2 this side, it becomes beta carbon, then gamma carbon, then delta carbon, like this we go, right? So yeah, will do sufficient examples. I just want you to focus on what I am discussing now. Okay, we'll do now that how to calculate alpha hydrogen and all. Okay, just 2 minutes. Okay, try to be here what we are discussing now, correct? So tell me, how many of you understood what is alpha carbon and what is alpha hydrogen? Because first of all, to understand hyperconjugation, you should know what is alpha carbon and alpha hydrogen. I'll take one example of this thing, carbocation also. Suppose I have this H, H and H, and here we have CH2 plus, okay? So this is alpha, this is carbocation, and the carbon attached to carbocation is again the alpha carbon. The next carbon is alpha carbon basically. Alpha hydrogen is the hydrogen which is attached to alpha carbon, Himanshu. Correct? Yes, all the hydrogen attached to alpha carbons are alpha hydrogen. Any other doubt? Okay. So first of all, you should know for hyperconjugation, we need alpha hydrogen. When you have alpha hydrogen, then we can draw hyperconjugative structures. Like we have resonating structures, okay? And hyperconjugative structure is because of this. What happens, this sigma electron comes over here, and this pi electron jumps over here. And it forms this, you see. This hydrogen and carbon will be as it is. This hydrogen will be here as H plus. It is present over there only. Double bond CH, single bond CH2, and negative charge on it. Okay. Now, since this sigma converts into pi, that's why we are calling it as sigma pi resonance, because it is one type of resonance only in which the sigma electrons are involved. Sigma electrons are converting into pi electrons. Okay, hence it is sigma pi resonance, right? H plus present here without any bond, and hence we call it as no bond resonance. Got it? No bond resonance. Now, if this sigma bond comes over here, this may also come over here, this may also comes over here. So with these three alpha hydrogen, we can draw three different structures. One is this and other one is this, where this sigma electrons comes over here and then this sigma electrons comes over here. All these are 1, 2, 3. All these are hyperconjugative structures. No, it is not bonded, but see, it happens very fast, very frequently. This comes over here, then again this comes over here, this goes over here. When this goes over here, then this comes over here, this goes over here, and this goes onto this electron pair. Means at a time, which sigma, this or this or this, which sigma comes over here, that we do not have any idea. It is possible that this may come over here, or this may come, or this may come. That's why we draw the structures with all these three sigma bonds. And 1, 2, 3 hyperconjugative structure here we can draw. Correct? You don't have to draw the hyperconjugative structure. Okay. Just you need to know how it is happening. Because when in the question, you should identify that hyperconjugation is possible or not. And based on that only, we'll do the, the answer of the question you'll write. No. H plus won't be attracted because the distance is not that small between this and this. Okay, it happens the change of sigma into pi is so fast that this H plus could not go anywhere. It will be there only. Right? So this is one thing. With carbocation also you see we can draw. This comes over here and it will be H, CH, H plus, double bond CH2. We can also draw another structure, you see, H plus CH, H, double bond CH2. One more structure we can draw where we have H, CH plus, H, double bond CH2. Right, possible. I'll give you the example, Anurag. Just 2 more minutes you give me. Okay, I'll give you the example. So all these type of hyperconjugative structure we can draw. Now, if they ask you this question, which is a very common question in this, number of hyperconjugative structure possible in the molecule, then it would be equals to the number of alpha hydrogen plus 1. The given one also we count, exactly same as we did in resonance. Are you getting it? Yes or no? Number of hyperconjugative structure is the number of alpha hydrogen plus 1. So how many hyperconjugative structure is possible in the first one? 4. How many hyperconjugative structure in the second one? Again 4, right? So number of alpha hydrogen plus 1 gives you the number of hyperconjugative structure. So this is the understanding of hyperconjugation. But again, I'm telling you, if you do not understand this, then also you can do the question in this way. How you see this? First of all, we'll do some practice for number of alpha hydrogen. For this given structures, you need to tell me how many alpha hydrogen are present. This one. This is the double bond. Tell me. Yes, possible, Shashwat. It only depends upon number of alpha hydrogen. If it is more than 5, possible. Okay, I'll do the first one, then you can try for the other questions, right? You see here, first of all, you count the alpha carbon. This is the alpha carbon, this is the alpha carbon, this is the alpha carbon, and this is the alpha carbon. And each alpha carbon has 3 hydrogen attached with it. Hence, the number of alpha hydrogen is 12. Clear? Is this the number of alpha? Is this the alpha carbon? This is the alpha carbon. This is the alpha carbon and this is the alpha carbon. And each of these alpha carbon has 2 hydrogen. So number of alpha hydrogen is 8. Could you tell me the alpha hydrogen in this? 3 plus 3, 6 plus 2, 8 plus 2, 10. Alpha hydrogen here is, this is alpha carbon, right? 3 plus 3, 6 alpha hydrogen we have. Alpha hydrogen here, this is the alpha carbon, this is the alpha carbon, this is the alpha carbon, and this is the alpha carbon. So 1 plus 1, 2, plus 2, 4, plus 2, 6. Last one, could you tell me? You just need to check the double bonded carbon. Adjacent carbon to the double bonded carbon is the alpha carbon. You see, these two are double bonded carbon, right? So all adjacent carbon to these two carbons are the alpha carbon. This. This is double bonded carbon. Adjacent carbon are this and this, alpha carbon. Alpha carbon is this two again. Clear, Shresh? 2 plus 2, 4, 5, and plus 1, 6. Anyone you can draw. See, for this, I'll take the simplest one, okay, to make you understand. Suppose I'm taking this one. If you want to draw the hyperconjugative structure, you write down the structure like this: carbon with 3 hydrogen, this carbon attached with CH2, and here we have the CH3. I'll draw one structure. Okay, you can draw all 6 structure because we have 6 alpha hydrogen here. So here the hyperconjugative structure would be this. This sigma comes over here, forms pi, and this pi converts into lone pair. So what we can write, H, C, H plus will be here, H, C, CH2, negative, and this carbon has 1 CH3. This is one of the hyperconjugative structure. Similarly, we can draw with this hydrogen, and this 3 hydrogen. Is it clear? Yes, total number of structures will be 7, 6 alpha hydrogen plus 1, the given one. Is it clear? Right? Now, on the basis of this only, sometimes they ask the question for stability of alkene. Stability of alkene is directly proportional to the number of alpha hydrogen because of hyperconjugation. Okay. No, it's not different. It's same only. All alpha hydrogens are same only. It's not different, but yes, we have movement of electrons continuously with different hydrogens, right? All the structures are exactly same. If you draw with this, with this three hydrogen, it will be exactly same. But since it is continuous movement of electrons, hence we have to consider all those. No, hyperconjugation means again that delocalization of electron, because you see the electrons are moving. No, so more delocalization, more stability. Anurag. No, because of delocalization, stability always increases. More delocalized structure, more stable the compound is. More hyperconjugative structure, more stable the alkene is. You must have get it in the other way. More distribution of electron, more stable the compound is. Yeah, you check it. Okay. So if suppose alkenes are given, suppose if I ask you the stability of alkene, we have this one, CH2 double bond CH2, then CH3, CH double bond CH2. Then we have CH3, CH double bond CH, CH3. Tell me the stability of these three alkene. Stability of these three alkene. The one which has more alpha hydrogen is more stable because of hyperconjugation. So number of alpha hydrogen here, could you tell me? Number of alpha hydrogen, 6. Number of alpha hydrogen, 3. Number of alpha hydrogen, there is no alpha hydrogen here, right? So stability order is this. Is the questions you are getting, so like the questions, to solve the questions very easy. But yes, since there are many things that you do not know, okay, there are so many things you should understand before this particular chapter. That's why in understanding the concept, like what is hyperconjugation, how to relate this, there you may have some difficulty. But if you take the keyword here, like alpha hydrogen you have to consider, then you can do this question easily. Okay. Did you get it? Okay, guys. So we'll take a break now. And after the break, we'll start with the comparison of the three, resonance, hyperconjugation, I effect, and then we'll see the application where we use all the three concepts. We are moving towards the last part of this chapter. Okay, again, let me tell you this. This chapter you have to do thrice, okay, before your exam. This is the first time you solve whatever assignment you can do, finish it. Those you are not able to do, let it be, just revise the theory. Okay, once we finish chemical bonding, then again you have to revise this chapter. I will let you know when you have to do what. Okay, anyways, take a break, guys. Now we'll start the session, resume the session at 6:40. Okay, take a break now. Hello. Shall we start? You there? Okay. So we have discussed the stability of alkene is directly proportional to the number of alpha hydrogen, right? Like we have other effects, resonance and I effect, hyperconjugation. Hyperconjugation also we have two types. Also we have two types. One is plus H and second one is minus H. Plus, like always, it is electron releasing. This is electron withdrawing. Okay. Plus H effect. One example you see. Suppose we have a benzene ring. It is exactly similar to resonance. Okay, plus M effect. You just need to know how to draw this. Again, you see this carbon is what? It is the alpha carbon with respect to this bond. It is the alpha carbon, right? Hence, it has 3 hydrogen, alpha hydrogen, and we can draw structures like this, hyperconjugative structures. And further, we can draw a resonating structure, which gives this. This is the hyperconjugative structure. Right? So from here we are drawing, this is resonating structure we are drawing here, right? From this to this resonating structure. But hyperconjugative structure, we can have with this and this also. So 3 alpha plus 1, 4 hyperconjugative structure we can draw. Now, one thing you take care of here, like we have in plus M effect, structure is no. Number of alpha hydrogen plus 1. No. See, this is just a second. Just a second. This structure is hyperconjugative structure, this one. So we can draw this with this hydrogen, and this hydrogen. So 3 such structures plus 1 given one. So hyperconjugative structure is always number of alpha hydrogen plus 1. From here to here, we have resonating structure. 1, 2, 3, 4. Why I have drawn the resonating structure here? To make you understand that because of plus H effect, the same thing we have written in plus M also, you see. Because of plus H effect, the electron density increases at what position? Increases at ortho and para, exactly same. Meta position is not affected by this. Meta position is not affected by this. Clear? No, hyperconjugation, because of this, it comes over here, and then we can draw the resonating structure. Because conjugation is there, so we are not doing anything into it. If conjugation is there, then the electron starts moving on this ring. That will lead to the negative charge here and here consecutively.
Sir, but then we can also have so like you drew the 4 resonating structures after the first one. So on the right H plus, we can have it on the top one and the left one also, right?
Right. I have drawn this 3 with respect to this. That's why I have taken like this. But you can take this bond pair also here, this bond pair also. Anyone you can take.
Sir, so in that case, do we take like totally? Then there will be 15 structures like which are possible. So
No. Actually, if they ask you the number of hyperconjugative structure, then it will be 4.
so they can't ask hyperconjugation and resonance happening at the same time.
If with this structure, they won't ask you the resonating structure. They won't ask you with this the resonating structure.
Yeah.
With this, they can ask you. But once they mention this, either the H plus will be here or here or here. Got it?
No, sir.
With this structure, hyperconjugation is there.
Yes, sir.
So they can ask you number of hyperconjugative structure for this one.
Yes, sir. But they can't ask resonating structure.
Yes, they won't ask you resonance over here.
Yes, sir.
If they ask you resonance, they may give you this structure. And with this, we can afford.
Yes, sir. That's what I meant. For the second structure, they can give either H plus on the right or on the top or on the left. Right?
Anything. But for all those H plus, we'll have 4 structure only.
Yes, sir. Got it.
Sir, but all those three resonating structures after the hyperconjugated structure, they also have H plus next to the carbon. So won't that make them also hyperconjugative structures?
No, actually, sigma to pi is what is hyperconjugation? Sigma pi resonance. Conversion of sigma into pi.
But it's also the no bond resonance, right?
Yes.
So won't those 3 be included then?
Just a second. Basic definition you keep in mind. Why it is no bond resonance? Because this bond is not present here, right? This resonance you can consider if one sigma bond is breaking. But here there is the sigma bond is not breaking here. It is pi sigma lone pair conjugation. That's why there is a resonating structure. Sigma to pi conversion is hyperconjugation. Hence, these two are hyperconjugating structure because sigma is converting into pi. Got it? Right? One more doubt. Orthopara things, Pranav, it is only defined for benzene ring, not hexane. Yes, that is right. Each hyperconjugative structure can have resonating structure possible. Resonance is always there whenever we have conjugation. The condition of resonance is satisfied, it is possible. That is it. Okay? Yeah, correct. Benzene, it's possible. Ortho para meta, it's only for benzene. Pranav, correct? Now, point I'm trying to make here is like plus M effect, electron density here also increases at ortho and para position. Meta position is not affected by this. Hence, hyperconjugation is possible only at ortho and para position. Okay, like we have in plus M. Similarly, minus H effect, you see, there is only one group which shows minus H effect. That is CCl3, minus H effect. Minus H effect, we have only one group. Carbon with Cl, Cl and Cl attached. This shows minus H effect. Only one group we have, not like we don't have any other examples of it. So in this, again, if you write down the minus H, so it withdraws electron from the ring. So this comes over here, and this sigma bond is taken up by this chlorine. Why? Because chlorine has vacant d orbital. So chlorine, carbon, chlorine, here we have Cl negative, and all other things will be as it is, you see. Here we have the positive charge and double bond. After this, you can draw the resonating structure again. This comes over here and you'll get the resonating structure. So you'll get the positive charge at ortho and para position in this. Yes or no, guys? Correct?
Sir,
Right.
so can we say that hyperconjugation influences resonating structures?
No.
So because when hyperconjugation happens, only then conjugation is possible within the ring, right?
It's happening because of conjugation. That is not the essential case. It's not like if hyperconjugation is not there, resonance is not there. We cannot say that. Okay. It is a special case. In this one, after hyperconjugation, resonating structure we are getting. So it is not, we cannot generalize this, that hyperconjugation influences this resonating structure in this. Okay. Right? Correct. Now, write down, because of minus H effect, what happens? Electron density at ortho and para position decreases. Write down. Electron density at ortho and para position decreases. Meta position is unaffected. Done. Meta position, again, it is unaffected. Okay. Now here, if I write down the application of it, application you write down, stability of carbocation is directly proportional to plus H and inversely proportional to minus H. Carbocation or free radical. Stability of alkene, I have already told you. Directly proportional to the number of alpha hydrogen. Okay. Now, whatever we have discussed so far, I'll write down here all together. Like for carbocation, you see stability of carbocation, we have seen it is affected by plus I, okay, plus H, plus M. Okay, and it is inversely proportional to minus I, minus H, minus M. Stability of carbon ion, if you see, directly proportional to minus H minus M, sorry, not minus H, because for carbon ion, hyperconjugation is not possible. minus I minus M plus I plus M. Carbocation, we can also write down here free radical. Both are same thing here. Did you get it? So now you see, this is the, for this thing, this relation, we have discussed all these things, resonance, hyperconjugation, I effect and all. So when you get the question in the exam, this is very important. Yeah, just a second, Anurag. When you get the question in the exam, okay, it is possible that in a given question, we have I effect, hyperconjugation, resonance, all things are possible. Right? All things are possible. Correct. So which one is dominating, that gives the final answer of that question. So you should know the dominating effect. Okay. You should know the dominating effect. In general, what we say, the priority order of these effects are done. Anurag, this one. The priority order is, you should keep this in mind. In general, the priority order is this. Priority order is this. Resonance dominates hyperconjugation, dominates I effect. This is the priority order we have. No doubt. Did you get the idea of it? How all the effects affects the carbocation stability? I'm just taking examples here, right? Acidity is also affected by all these factors. Okay, we'll discuss questions on that. Okay, can I go to the next page? Yeah. Okay. Now, you see the application of this. Just a second. The example that we are going to see now, it includes all the electronic effects. It includes all the electronic effects here. Okay. Look at this first of all. Suppose you have this one. The stability of carbocation. There are certain factors which stabilizes the carbocation, and there are certain factors which destabilizes the carbocation. Okay. The first factor we have, and this is in priority I'm going to give. Okay, in priority. We have first one, we have part of aromaticity. Means if the carbocation is a part of aromaticity, it is the most stable carbocation. Then the second factor is plus M effect. Third factor is plus H effect. All electron releasing factors are there. Then we have plus I. Then we have hybridization. Sixth factor we have minus I. Seventh one we have minus H. Eighth one we have minus M. And the ninth one we have is a part of anti-aromaticity. Did you get this? Means this is the order will follow for the stability of carbocation. Overall order is this. Yeah, free radical also we can think about. Fine, Anurag. Okay. From this to this are stabilizing factor. All these are stabilizes carbocation. Stabilizing factor. From here to here, it is destabilizing factor. Destabilize the carbocation. Are you getting it? What are we doing? First, we have discussed all these effects one by one: I effect, resonance, hyperconjugation. And since all these effects affect the stability of carbocation, carbanion, acidic order and all, so we have to see the, the overall order is what for the stability of carbocation. This means what you get, suppose three compounds of carbocation. In the one compound, the carbocation is stabilized through plus M effect. Other one plus H effect. And the last one plus I effect. Then which one is more stable? Which one is more stable? The one which shows plus M. That is what it means. Okay. So now the most important part of this chapter we are going to see is this. Okay. It revises all your concepts. Whatever you had done so far, we have done so far. All the concepts it revises. Okay. So the first question you see, we have a ring. And on the ring on the top, we have CH2 plus carbocation. Again, depending upon the difference in the structure, we'll find out the stability. Do we have any difference in this one? Now you see, how do we do this question? So this kind of question, first of all, we'll assign the effect. What effect CN shows? Could you tell me? What effect cyanide group shows CN? CN shows minus M, OCH3 shows plus M, NR2 shows plus M, and this shows minus I. Okay, this shows minus I. Minus M effect destabilize carbocation. Minus I destabilize. Plus M stabilizes the carbocation. So which one has more plus M effect, NR2 or or OCS3. Nitrogen becomes lesser electronegative than oxygen, hence it has more tendency to lose electron. So plus M effect of Nr2 dominates the plus M effect of OCS3. The effective order of stability of carbocation is, this is the most stable one, then this one, then third one, and then we have this one. This is the fourth one. Order of stability is this. Is it clear? Okay, this one you see. We have CH2 positive charge. Here we have NH2. Just assign the effects first. If you get the effect right, you will get the question right. Okay. If you made some mistake over here, you won't get the answer. OH and CH2 plus chlorine. Tell me the order of stability of this. Okay. Now you see, could you tell me the effect here? What effect we have in the first one? Plus M. Here again plus M minus I for chlorine. Okay. OH and NH2, which one has more plus M effect? NH2, right? Because less electronegative nitrogen. Hence, this 2 stabilizes the carbocation. This destabilizes the carbocation. So obviously this is 3, this is 2, and this is 1. Clear? This position, CS3, what effect we have here? Para position. Para position, we have plus H, plus M is not possible here. How it is plus M possible? Carbon does not have any lone pair, no? Right? Plus H. What effect we have here? Plus I. Why plus I? Why not plus H? Because it is meta position. At meta position, only I effect possible. Okay, only I effect possible, right? So plus H dominates plus I. So A is more stable than B. Any doubt? Where resonance is possible? Now position matters, but we have hyperconjugation now. Hyperconjugation always dominates I effect. Both are a stabilizing factor, but this will stabilize more than this. Hence the order is. Resonance is not possible with this CS3. CS3 does not show mesomeric effect. Did you get it? Clear? Now suppose in this only one more molecule is given, and which is this. In this, one more molecule is given, which is this. We have CH2 plus on the top, and here CS3 added. Now tell me the order, A, B, and C. Write down this question again, right? 1, 2, and 3, all these three write down again. Okay, don't make changes into this. Okay, why C is more stable? No. The logic is not correct, guys. See, I'll explain. First of all, what we do, we assign effect. What effect we have here? What effect? H plus H, correct? Now, here we have plus H, here we have plus H, correct? And this is plus I. So obviously these two are more stable than this one. So one thing is sure, that this is the third one. Would you agree with me on this? Correct? Right. Now in this two, since both shows plus H, so we cannot decide on the basis of plus H, because hyperconjugation has nothing to do with the distance. It only requires conjugation. It has nothing to do with the distance, right? So we cannot decide one and third which one is more stable with respect to hyperconjugation. Then we can see the next effect which is possible. This CS3 we know it also shows plus I effect. This also shows plus I effect. Are you getting it? CH3 we were talking about only dominating effect here. But apart from this plus M, you see this NH2 also shows minus I. Since plus M dominates minus I, so we consider this effect over here to find out the answer. But here in this question, what happens? Both shows plus H. So we cannot decide on the basis of plus H. Then we'll check the next effect, which is plus I, correct? Okay. So plus I, at which position it is more effective, plus I? This position or this position? Ortho, right? Because it is closer to this CH2 plus. And plus I is the dominating effect, closer to this. This one is slightly more acidic, stable than the first one. Hence, the order of stability is 1, this is 3, and this is 2. Are you getting it now? Is it clear? Are you getting it? Okay, this question you see. Check your notes, Pranav. All of you draw the structure and then write down the answer. The stability of carbocation. Stability of carbocation you have to compare. OCS3, what is the condition of plus M, Pranav? If you try to memorize it, you will not get it. I have given you the condition. If the first atom has lone pair on it, it shows plus M effect. And oxygen is more electronegative than carbon. So OCS3 shows minus I, plus it also shows plus M. In plus M, I have given you this. That's what I said. OCS3 shows minus I and plus M. But plus M dominates minus I. You asked me about OCS3, correct? So I have given you the answer with respect to OCS3. Now it is at meta position, so resonance is not possible. Minus I is possible. I told you what are the possible effects for OCS3. It is minus I and plus M. Now depending upon the position of OCS3, we can find out the effect. Fine. Meta is always I effect. Meta always I effect. Done, all of you? Okay. Tell me the effect at this position. Meta, it's minus I. Ortho, it's plus M. Plus M dominates minus I. So this is more stable than this one, 1 and 2. Okay. Here what effect we have? What effect we have here? Tell me. Plus I is possible, but plus H is also possible. Right, because we have one alpha hydrogen here. Plus H possible. Here what effect possible? Okay. At this carbon, there is no hydrogen present. So it shows plus I only. Here we have plus I. Here we have.
Sir, in this case, for H plus effect, shouldn't be adjacent to the carbon which is having a double bond.
So this carbon is double bond. Adjacent carbon is this.
Okay, fine.
What?
Sir, I got confused. Okay, I was talking about the second one. I just got confused.
Is it clear? The second one, here we have plus I since no alpha hydrogen present. Here we have one alpha hydrogen. Hyperconjugation dominates I effect this. Number of alpha hydrogen here, 2. Number of alpha hydrogen here, 2. So we cannot find out with respect to alpha hydrogen. I effect for this group is more than this because it is larger group here, right? This is more stable than this, plus I nature is more for this group. Yes, Anurag. What effect we have here? 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 Minus I. This is stabilizing factor. Most stable is this. In this two, these two are destabilizing factor. This dominates, right? This is second. This is third. This one you tell me. Which one is more stable? Why A? Because here we have plus H minus H. This two. Which one is more stable? B. Okay. You see, this compound is conjugated 246 6 pi electron conjugated. It is aromatic in nature. And this carbocation is resonance stabilized. Now you look at the order of stability here. You see this order. When positive charge is a part of aromaticity, it is the most stable one, right? Hence, for this question, you see, for this question, this is aromatic carbocation, this is resonance stabilized carbocation. Hence, the first one is more stable than the second one. Okay. Now in this one also, suppose if I write one more compound, which is this positive charge, then what is the order? Okay, you see in this one, this compound is also aromatic. Conjugation with 2 pi electron, Huckel's rule, right? So obviously aromatic compounds, carbocation is more stable, right? So one thing is for sure that this is the third one we have. This is also aromatic, this is also aromatic. Here we have larger conjugation, right? Here we have larger conjugation. Hence, this one is more stable than this one. Did you get it, guys? All of you understood this? So higher conjugation means what? When you draw the resonating structure of this, no? You'll get more number of resonating structure. 6-membered ring, not 6, 7-membered ring. This is only 3-membered ring. You'll get 3 resonating structure here. You'll get 7 resonating structure here. So more resonating structure means what? More delocalization of electron and hence more stability. Clear? Okay. So this is it, guys, for today. Okay. We have few more things that we have to see. Only examples we have seen carbocation. Similarly, for carbanion we'll see and other things also. Okay. So next class in 1.5 hours, we'll finish this chapter and we'll start with a new one. Okay. Assignment given on Learnist, please do that. And all these examples that I have done, all are very, very important examples. It clears your concept easily. Right? So revise it properly. No, this is not coming for the test. For the test, you have some basic concept. The first chapter plus nomenclature. This GOC is not coming for the test. I'll let you know the next chapter next class. We'll let you know regarding that. Okay, guys. Thank you. Take care. Bye. Yes, only mole concept and IUPAC. Thank you.